So the topic for the lecture today is type system. And also we will look at beta reductions and eta expansion. So previously we formulated natural reduction system using truth judgment. And when we applied Curry-Howard isomorphism, and we formulated the natural reduction system using proof term of type A. So this proof term is a compact representation of this proof, and we can consider this A as a proposition here, but the same A here as type. So proof corresponds to proof term or program. This is called proof term. Now, we'd like to repeat the same exercise starting from hypothetical judgment. So we have hypothetical judgment of this form: A1 true, AN true, and you have turnstile and C true. So you have natural deduction system formulated with this hypothetical judgment. So you have a proof D, and we'd like to represent the proof D with proof term M of type A, but under typing context of this form, X1 has a type A1 through Xn has a type AN. And this one is called type binding because variable X1 is bounded to type A1. And this one is called typing context. So typing context is a collection of type bindings. These are type bindings, and their collection is called typing context. So starting from this hypothetical judgment dealing with truth judgment, we apply Curry-Howard isomorphism, and you obtain another form of hypothetical judgment, which is called typing judgment. So essentially, you reformulate a natural reduction system using typing judgments, and the resulting system is called type system. Type system. So here we use entailment relation, and here we use the entailment relation. So essentially, there's no difference between this formulation and this new formulation. The only difference is superficially here we use this proof, whereas here we use the proof term. That's all. That's what is guaranteed by the Curry-Howard isomorphism, under which, well, these proofs and proof terms are indistinguishable, and these propositions and types are indistinguishable. So that's the basic plan. So let's try to translate the rules, the inference rules in this system to obtain inference rules in this type system. So later we will call these inference rules as typing rules. Typing rules. So let's do this. So first, from this system, we have this inference rule, hypothesis rule. So gamma, under gamma we have A true if A true is one of the hypotheses. So that's the hypothesis rule in this in this formulation of proportional logic. And the corresponding rule is we reuse the same meta variable gamma, and this time this gamma is collection of type bindings of this form. Here, gamma is a collection of hypotheses, A1 true, AN true. But here, gamma is collection of type bindings. You have to assign a proof term for this proposition A1, but it's a hypothesis, so its proof term is actually unknown. So you introduce a variable. So we reuse the typing context the gamma, the meta variable here, but it's interpreted differently. So under this typing context the gamma, we can deduce X has a type A if X colon A, this type binding is actual member of this typing context. And we use this one, we call this rule hypothesis rule. So essentially there is no difference. This rule says if A1, this rule says if A2 is a hypothesis, then you may deduce it. This rule says if this type binding is one of the assumptions that you make, then you may deduce it. So essentially there's no difference. So from the hypothesis rule in logic, we obtained a typing rule of the same name. Now let's translate implication introduction rule. You have A implies B true, this implication introduction rule. Under extended typing context, if you can deduce B true, then you may deduce A implies B true. So let's do this. So the idea is every hypothesis will be assigned a variable to represent its proof. So gamma is translated to gamma. It's a bit confusing, but we decided to reuse the same meta variable gamma for this typing context. And for this A true, we introduce a variable X of type A. And suppose that the whole proof, the whole derivation tree, which deduces B true, can be represented with a proof term M of type B. Then, under typing context the gamma, we should be able to find a proof term of type A implies B. And we decided to use the syntax for simply typed lambda calculus. So it's going to be lambda x colon A dot M. So this basically, this proof term now represents the whole derivation tree here. And we call it implication introduction rule. Now let's look at implication elimination rule. If Emma proves A implies B true, and if we have A true, then apply implication elimination rule to deduce B true. So we translated these judgments inductively. So this one produces gamma M A implies B, and let's say this one produces gamma B has a type A. And then by combining these two, we should be able to obtain a proof term of type B. And we decided to borrow the syntax from the lambda calculus. So we use this lambda application. So this lambda application M applied to N is going to have type B. And this is also called implication elimination rule. And we can repeat the same exercise for the remaining inference rules here, and then we can derive the corresponding typing rules. So let me just show you the typing rules that we can obtain in this way. So for conjunction introduction, suppose that M has a type A, and under the same typing context, N has a type B. Then we can pair them up to produce a proof term of A conjunction B. So here we use the same typing context because you can recall that in the original formulation using hypothetical judgment, we had something like gamma A true, gamma B true, then gamma A conjunction B true. So even in the original inference rule, we used the same set of hypotheses. So similarly here, we use precisely the same typing context. So this is going to be conjunction introduction rule. For conjunction elimination rule, suppose that we have M of type A conjunction B. This is, and then we can apply projection operator obtaining the first element, and then it's going to have a type A. This is the conjunction elimination rule, left rule, and there's symmetric case conjunction elimination right rule. What about disjunction? Suppose that M has a type A, then we can obtain a proof term of A disjunction B by applying disjunction introduction left rule. And here we use injection left term. But without this annotation, the type is ambiguous. So we should place a hint here so that we can obtain this type B. So we annotated this injection left with type B. This disjunction injection left rule, and there's a corresponding disjunction introduction right rule. So what about disjunction elimination rule? So it's a disjunction elimination rule. So you start with a proof term of type A disjunction B. So the idea is we consider two branches. The first branch assumes some proof term of type A. So it goes like assume X as a type A, and then we can deduce another proof term of type C. And the other possibility is M was created from a proof term of type B. So let's just say the proof term is Y. So this proof term Y has a type B. Let's just say, and then we can obtain another proof term N prime of the same type C, as shown over here. So these two types are the same. And then we can obtain a proof term of type C, whichever branch we take. And we borrow the syntax from the lambda calculus. So we perform case analysis on proof term M. If this is injection left, then we take N. And if it is injection right, then we take this proof term N prime. So of course, inside the proof term N, you may see instances of this variable X, maybe 0 times, or 1 time, or many times. And likewise, inside this proof term N prime, you may see instances of this variable Y. For top introduction rule, you have a unit which is type top. And this bottom elimination rule, suppose that if you have a proof term of type bottom, then you can prove anything, or you can produce a proof term of any type C, and which the syntax abort. So that's how we derive these typing rules or the inference rules based on this typing judgment. So we systematically derived all typing rules or inference rules in this type system by applying Curry-Howard isomorphism again to this natural deduction system formulated with this hypothetical judgment. Now let's consider structural rules and substitution. So we learned that given a system of proportional logic, for example, we can consider structural rules such as exchange, weakening, and contraction. So here we assume this entailment relation gamma A true, this hypothetical judgment. And we also consider the two principles, reflexivity and substitution. So we learned that this reflexivity and substitution are called principles, which implies that they must hold. They must hold for any system based on this hypothetical judgment. If these two principles do not hold, it means that there's something wrong, fundamentally wrong, with the way that you use this hypothetical judgment. On the other hand, for these structural rules, it's optional to choose this exchange property, for example. So in other words, you may or may not choose to include this exchange property or weakening property or contraction property. It's up to you. In the case of proportional logic, we decided to include all these three structural rules. Now, from the system based on this hypothetical judgment, we derived a typing system which is based on this typing judgment, where this typing context is a collection of type bindings of this form. And we can present precisely the same argument. There got to be some principles called reflexivity and substitution, and these two principles must hold. If they fail to hold, then there's something fundamentally wrong with the way that you use this typing judgment. On the other hand, for these structural rules, you may choose to include them or exclude them. But in our case, we decided to include all of them. For example, let's assume that exchange is built in the use of this typing judgment, which means that if gamma is a collection of x1, a1 through xn, an, we assume that this exchange is built in. So the ordering of these type bindings is immaterial. You may exchange them as you like. It doesn't change the meaning of the judgment. So exchange is already considered. Now we can discuss weakening property and contraction property in this typing system. And also we should, of course, prove that substitution principle. Reflexivity is obtained for free because we have this hypothesis rule, gamma xa, if xa, this type binding, is an element of gamma. So this hypothesis rule allows us to obtain this reflexivity principle for free. So this is gone. So we don't have to consider it. And we decided to interpret this gamma as unordered collection of type bindings. So exchange is gone. So let's discuss weakening and contraction and substitution on this typing system, just like we considered these properties and principle on this proportional logic. So for weakening and contraction, we can state them as like weakening. Under typing context, the gamma M has a type A. Then we can weaken the whole statement by adding an extra type binding here. let's say this is C, we add an extra type binding here, and still we should be able to show that this proof term M has a type C. And this is weakening because the statement here, the whole statement here is weaker than this one. This is you can think of this M colon C as the goal, and this is the assumption that you start with. But now you start with more assumptions than previously. So essentially, you are trying to prove an easier problem. So in this sense, this property is called weakening. Contraction, if you have two copies of the same type binding here, and then you can contract them into a single instance. So then XA turnstile M colon C. So this is a contraction property. So remember that we assume exchange is built in, so the ordering of these type bindings doesn't matter. So the proof is straightforward. You can apply rule induction on this judgment or this judgment, or alternatively, you can actually perform structural induction on this proof term. And the reason why it works is this proof term M essentially represents the whole derivation tree in a compact way. So either you can apply rule induction on the whole judgment, or you can analyze the structure of this proof term M. In the end, you will find that the two approaches equivalent. And substitution, substitution is stated as follows. Suppose that you have a proof term of type A under typing context gamma. And now you extend the typing context with a variable x of type A. And under this extended typing context, you have a proof term of type C. Then the substitution theorem, this time we will call it substitution theorem. Then you may substitute this M for variable x inside this proof term N, and still you have the same type C. This is substitution theorem, which is precisely what you saw in the programming language course. So back in the programming language course, we went to length to define this operation, substitution. And we also learned that the precise definition of a substitution is quite subtle because of the phenomenon called variable capture. So in order to deal with this phenomenon called variable capture, we had to define this substitution as capture avoiding substitution. Or what that means is that you might have to rename bound variables, or in the technical jargon, apply alpha conversion. So we have seen the definition of a substitution and also the proof of a substitution theorem in the programming language course. And we are witnessing essentially, actually precisely the same statement here. But the motivation is quite different. Previously, we wanted to design and implement a programming language. This time, we'd like to investigate proportional logic. But by exploiting this proof term, it's easier to deal with this proportional logic because these proof terms are essentially representations of proofs. So that's the idea. So the proof of this substitution theorem proceeds by rule induction on this judgment. So the proof is also the same as we have seen in the previous course. So this concludes the development of type system, which uses this form of typing judgment, where this gamma is collection of type bindings, say x1, a1 through xn, an. So superficially, this typing judgment seems to have nothing to do with this proportional logic, but we learned that it is actually just another presentation of this hypothetical judgment in the proportional logic. So starting from the proportional logic, you applied this Curry-Hall isomorphism, and then you obtained this typing system. This is a type system, which is the basis for the static semantics in the programming languages. Now let's talk about operational semantics. So the question now is, now that we have seen the logic, this proportional logic, in conjunction with this Curry-Hall isomorphism, gives us a very nice theoretical foundation for this type system. And the question now is, what about this operational semantics? Can we identify some phenomenon or some principle that provides us with some foundation for this operational semantics from this logic? So what is the foundation of this operational semantics? And the answer is local reduction and local expansion that we have seen previously. But the idea is that now we know the notion of local reduction and local expansion. We'd like to apply Curry-Hall isomorphism again to these two notions, local reduction and local expansion. In the end, we obtain something called beta reduction and eta expansion, which you should be familiar with if you have taken the programming language course. And by composing these beta reductions, we obtain reduction strategy such as call by value, call by name, or call by need, etc. So the story is precisely the same. We know this local reduction, what this local reduction is. It is basically something introduction followed by corresponding elimination right away. And this is, we decide to call this a detour, because eventually you prove the same judgment to see true, but you decided to take unnecessary detour here by applying introduction rule only to find another corresponding elimination rule applied immediately. So this is a kind of a detour, unnecessary. So by eliminating this detour, you were able to reduce the complexity of the proof in some sense. So previously you have a detour here. Now the detour is gone. So the proof has reduced in complexity. So this is the way that you eliminate the detour. And we'd like to translate this whole phenomenon, interpret the whole phenomenon in terms of proof terms. So let's do this. But the idea is simple. Local reduction, it's introduction, for example, conjunction introduction, followed by conjunction elimination. And this is a detour, and we can get rid of it, thus reducing the complexity of the derivation tree. And what would happen if you formulate this phenomenon, local reduction, in terms of proof terms instead? So let's take a look at an example. Conjunction. In the case of conjunction, the introduction rule looks like a true be true, and then you conclude A conjunction be true. This is a conjunction introduction rule. And then in order to contrive a detour, you apply the elimination rule. Let's just say conjunction elimination left, and then you have A true. Let's say this is D and this is E. By local reduction, this is a reduction, you can obtain the proof of A true without taking this detour by just copying this proof D. Now let's reinterpret the same phenomenon in terms of a proof term. So we have a proof term M of type A. So this corresponds to M. And we have another proof term N of type B. So this proof E corresponds to N. And then you have M and pair of M and N of type A conjunction B. This is the conjunction introduction rule. Now let's apply conjunction elimination rule, and you have first M N of type A. This is conjunction elimination left rule. So this is the detour. Now I would like to obtain a proof term of type A without taking this detour. Then the answer is pretty easy. You can just copy this proof term M. So now we see that the whole derivation tree, this proof, has been reduced to this smaller proof tree. Or equivalently, this proof term has been reduced to this proof term. So we can summarize the finding with this beta reduction. So first, M, N reduced to M on the beta reduction. So to indicate it is a beta reduction, we use this symbol. So this proof term beta reduced to this proof term M. So basically you can repeat the same exercise. So for example, in the case of implication, you start with a proof term of A implies B. So this is implication introduction rule. So you have lambda abstraction. And then we see another implication elimination rule. So let's just say N has a type A. And then you obtain a proof term here of type B, and it is lambda application, lambda x A dot M applied to N. So N comes from here. Now, this is a detour, implication introduction followed by implication elimination rule. So how can we reduce it? So we are supposed to find a proof term of type B without taking this detour, without introducing lambda, and without using this lambda abstraction, lambda application. Without using lambda abstraction here, and without using lambda application here. So the idea is we make a copy of this proof term M, but M may contain instances of this variable X. So now we are going to substitute N for this variable X, which is safe because this type binding assumes a type A, and this proof term N happens to have the same type A. So the idea now is we take this proof term M and replace this variable X with this proof term N. Now we have another proof term of the same type B. And this proof term does not contain this detour. If you have this detour, you have to have this lambda abstraction and lambda application. But now you don't have this lambda abstraction and lambda application. So to summarize this finding, we have is beta reduction. Lambda xa dot m applied to n, beta reduced to n for xn. So this is basically a function call. This is the function. This is the function argument, and this is the result of a function call. Now you can compose this beta reduction in particular strategy, in a particular order. Then you obtain this so-called reduction strategy, such as call by value or call by name. And similarly, we can obtain the beta reduction for case term. Suppose that you have some injection left m. So this is basically the result of applying disjunction introduction rule. And this case term is basically the result of applying disjunction elimination rule. So we have this detour, introduction followed by elimination rule. So if this is injection left xn or injection right y of n prime, then you automatically take this left branch because it's clear from the syntax. You have created this proof term by applying injection left. So you have to take this branch. So you somehow perform pattern matching against this pattern. So x is going to assume this proof term m. So you end up with n where x has been replaced by m. So this is a beta reduction for injection left. And there's a symmetric case for injection right. So in this way, we obtained the beta reductions for proof terms, beta reductions for this product, this conjunction, and beta reduction for implication, and beta reduction for disjunction. And previously in the programming language course, we learned this type preservation. So basically what that means is, if an expression E, a program E has a type A, and E reduces to E prime, then it must have the same type A. E prime must have the same type A. So this is part of a type safety. So in the case of the language that we developed so far, based on proportional logic, we call this property subject reduction. Subject reduction means the type doesn't change even if you apply this beta reduction. So for example, M has a type C, and M beta reduces to M prime, then we can expect M prime has the same type C. So it's almost like the type preservation theorem that we have seen in the previous course, but there's a minor difference because here we assume beta reduction, and this is just a reduction. For example, this is not necessarily beta reduction. This can be just a function call, because here we assume some particular reduction strategy, such as call by value or call by name. Other than that, the two theorems, the type preservation and subject reduction, essentially stated the same, describe the same phenomenon. So we can also prove this subject reduction. The last topic is local expansion. Local expansion and eta expansion. So the idea is the same. In the previous case, we started with a local reduction, and then we obtained this notion called the beta reduction. And likewise, we start with this local expansion dealing with the proof derivation tree or proofs. And then we can obtain eta expansion, which deal with proof terms. So here's an example. Suppose that we have M of type A implies B. The goal now is we'd like to expand it, eta expand it. So we use this subscript eta. And we'd like to obtain essentially a proof term of the same type A implies B, but this time by applying elimination rules. So it turns out that, so basically you'd like to build another proof term or another lambda abstraction, because the canonical form of a proof term of this type A implies B is a lambda abstraction. So perhaps you are expecting some lambda abstraction here. And it turns out that the result of this eta expansion is a lambda abstraction of type A implies B. So X must have type A, because it means this type A implies B means the argument has a type A and the return type is B. So the argument X is going to have type A. Now you have to build a proof term of type B. But it's pretty easy because you have a proof term M of type A implies B and X as type A. So you can use X as the argument to this lambda abstraction. So the body is going to be MX. So this is the eta expansion for this implication. So that's precisely what we saw in the programming language course, this eta expansion. And similarly, we can derive A conjunction B. Now you have to obtain A conjunction B, a proof term of type A conjunction B. But the canonical form of proof term of A conjunction B is a pair. So, but the first one can be obtained first M, and the second component can be obtained as a second M. So first M has a type A, second M has a type B. So you pair them up and then obtain a proof term of type A conjunction B. In the case of disjunction, you intentionally perform case analysis. So you perform case analysis on this proof term of type A disjunction B. If this was injection left, then perhaps this one has a type A because this is injection left. And then now you have to build another proof term of type A disjunction B. And it's pretty easy. You just take injection left A with annotation B. Then this one has a type A disjunction B. If this proof term was injection right, let's say call Y, then this Y is going to have type B. Now you have to create a proof term of type A disjunction B, which is pretty easy. You just take injection right with Y and annotation A. And this injection right Y is going to have type A disjunction B. So whichever branch you take, you always end up with the proof term of A disjunction B. So the whole proof term is going to have type A disjunction B. So this is the eta expansion. Finally, we have this funny eta expansion for top type and this bottom type, this eta expansion. And here you abort M, and it's going to have a type whatever comes here. So we just annotate abort with the top bottom, and then it's going to have a type bottom. So we have derived these eta expansions from local expansion. So now we can see the big picture here. You started with some sort of logic here. In our case, it was a proposition logic, purely stated in terms of truth judgment. And then we reformulated this logic using this hypothetical judgment, which facilitates reasoning because it automatically keeps track of the scope of every hypothesis for you. So this is a syntactic convenience, but nothing new. There's no new notion here. And then you applied Curry-Horde isomorphism. And first you obtained this typing judgment or type system. And we also have seen subject reduction. So perhaps this is the foundation for, you can use this type system as the foundation for the type system of your programming language. And from local reduction and local expansion, you apply the Curry-Horde isomorphism and you obtained this beta reduction and eta expansion. And perhaps this is the basis for subject reduction actually. Should combine these two. So perhaps you can use this beta reduction and eta expansion as the foundation for this operational semantics for your programming language. This for typing system, type system or static system, static semantics for your programming language, and this for the operator semantics. So we see the close connection between logic and programming language here, very strong connection, and the principle that connects these two different worlds is Curry-Horde isomorphism.